The second example about the moving charged particle in the magnetic field is actually very crucial for us. We all know that the different sources in the universe will produce the cosmic ray. What is a cosmic ray? Cosmic ray is nothing but just a bunch of the charged particle moving. So if we don't have the magnetic field produced by the Earth, ideally all the cosmic ray particles which carry a very big energy will just arrive at the surface of the Earth and interact with our body directly. But fortunately, in our previous lecture, we know that the Earth has its own magnetic field, and the direction of magnetic field is from the north here, which is the geographical South Pole. So they will start from here and end at the South Pole here. So it is because of the magnetic field of the Earth, they protect us from being interacting directly with the cosmic ray. And the simple explanation is better use the magnetic force we just learned. So let's think about that. This is the magnetic field lines of the Earth, and you have a bunch of the charged particle moving, coming from different sources and hitting on the surface of the Earth. However, we know that the charged particles will experience a force when they are in the magnetic field. So let's use these pictures and you have a sense of feelings. So let's assume that you have a positive charge moving from this direction and hitting on the surface of the Earth. So when they comes to these regions, they will experience a magnetic field produced by the Earth. And using the right-hand rule, because the direction of a current is in these directions, and the magnetic fields at this particular point is in these directions. Agree? So therefore, if you point your four fingers, which is the direction of current, which is toward these directions, and the magnetic field is these directions. So you will find out when you curl the finger, actually there is a deflecting force acting on the charged particle in these directions. So this explains why that when the particle try to enter and interact with the surface of the Earth, they cannot reach. They will be deflected away from the surface. So this is a very crucial example to understand why the charged particles cannot hit the surface of the Earth. So now let's try to have our first conceptual quiz today. So this is not a difficult one, but you should think about that. What is the direction of the magnetic force with respect to the direction of the charged particle? So the answer is B. They cannot change the speed of the particle because they cannot accelerate the particle. They can only change the direction. They deflect it. And the reason is because the force is perpendicular to the movement of the particles. So the force they produce is also perpendicular to the direction of motion, and based on the Newton first law, you cannot accelerate the particle in that direction. The third example is the electric motor, which is very important to our life. Yeah? When you are driving a car, the most crucial element is the motor inside. But we can also try to understand a very complicated structure using the principle we just learned. For sure, I already simplified the pictures. So what happens is that when you press the gas will start to produce a current. So you can consider when you press the gas, you provide a voltage difference and the current start to flow within the car. Now, when the current flow and passing through the engine, which is the motor, they have the structure similar to this one. There's a magnetic field within that, but there's a bunch of coils which can rotate. And the current will flowing through the coils within a closed loop, which is a closed circuit we have learned before. And because the current passing through the coils will interacting with the magnetic field here. So here it is North Pole on the top and South Pole at the bottom. So the magnetic field is downward. So we already learned that from our previous lies that we know if you have magnetic field and the current passing through, they will experience a force. So I will show you in the next slide that there will be actually two forces acting on the coils with the current. So the force on this side of the coil is upward, and the force on this side of the coil is downward. So therefore, when you create a current, and this current passing through the coils, the result is the coils will continuously rotate, and this is the reason why your tires can be rotated. So let's try to look at about more clear pictures about what really happened there. So if you produce a magnetic field in these directions, and now you want to rotate the force in the clockwise directions, so you have to produce an upward force on the left side of the coils and downward force on the right hand side of the coil. And the question is that, then what is the direction of the current right now? So if this is the direction of the B field, and this is the direction of the force, then please think about it. This is the thumb of your right hand. So you will find out that in order to create an upward force, the current should be flowing from this end to this end. So this is the direction of the four fingers of the current, and they will curl to the direction of B field. This is direction field. So you curl your forefinger to the direction of B field, and the thumb is upward. So the direction on this end of the coil is from this end to this end. On this side of the coil, now the current will be from this end to this end, such that it will produce a downward force. And now these two forces will not balance each other. Instead, they will produce a torque. So that's the reason they start to rotate. So now, in the future, you will have a better understanding how the motor was designed. Now, let's study about the next concept, the topic, the electromagnetic inductions. So these three gentlemen are the one trying to formulate the formula. So you can find out that based on the history, people start to study about the electric field and magnetic field around the 18th century to the 19th centuries. So what is the electromagnetic inductions? So Faraday and Henry find out that if you don't connect the wires, the coils to a voltage difference, then ideally there's no way there's a current can be produced, or the voltage difference can be produced. But they find out that actually there's a induced voltage if you change the magnetic field passing through the coils. So what does it mean? So think about that. Now you have a bunch of coils connected to the galvanometer. This is just a device which can measure the direction of current. So originally you don't have a magnet here. So if you connect the coils to this device, you will not measure any current. But people find out that is, if you try to bring a bar magnet toward into the solenoid coils or away from the coils, you will find out there will be an induced current produced. And we know that if there's an induced current produced, there will be an induced voltage. So this is not an easy thing because they involve a lot of the directions. So I will give you more introduction to that. So people, when they conduct the experiment, they find out there are several factors will decide how strong the induced voltage will be. So the first, they find out if you increase the number of the coils of the loops, then the bigger the induced current and induced voltage. Or it also depends on how fast the magnet entering to the coils or leaving the coils. So which means is how fast you change the magnetic field within the regions. So here you will find out, not a surprise to you, if you have a slow motion of the magnetic field, you will produce a very small voltage, induced voltage. But if you try to move the magnet rapidly into the coils, you will produce a very big voltage. So this kind of inductions happens no matter what kind of structures. So it is intrinsically related to the thing we have studied before. So for example, if you have the two loops of the coils here, and you try to insert the bar magnet, you will produce induced current and induce the voltage difference. If you now try to increase the number of the loops, the bigger the current and the induced voltage will be produced. So more loops, more inductions. That is what we mean the induction. It is the induced current and induced the voltage will be produced. But I have not yet teach you about the directions, so I will show you in the next few slides. But now let's try to study about the second conceptual quiz. So the answer should be A. So a voltage will be induced if the magnetic field change. So it is irrelevant to the electric field. And also, if you have the B field, but if it doesn't change, it still cannot produce the induced magnetic field. Induced the voltage. So now, let me show you that how to determine about the directions. So the directions of the induced current is this. The nature do not like the change. So originally there is no magnetic field here. So if you try to insert a bar magnet, which means the magnetic field here will become stronger and stronger. Yeah? So therefore, the nature will produce an induced magnetic field. And the direction of induced magnetic field is north pole here and south pole here. So if the induced magnetic field is north pole here, then north pole and north pole do not like each other. So therefore, they will try to stop and prevent the bar magnet from moving in. And because this is a coil, do you remember that I showed you that how to use the right-hand rule to determine that if you produce a B field within the coils, then the thumb is the directions of your magnetic field, and the four fingers will be the directions of your current curl around the coils. So therefore, now you can find out the direction of the induced current. Vice versa, if you have the bar magnet, now it's trying to moving away from the coils. So which means originally you have the magnetic field here, but now it becomes smaller and smaller. Once again, the nature do not like it, so they will produce an induced magnetic field, try to stop and prevent the bar magnet from moving that. So therefore, now when the bar magnet is moving away, they will produce an induced B field. Now, the direction of induced B field is south pole here and north pole here. And we all know that north pole likes south pole. So the induced magnetic field will try to attract the bar magnet back. So therefore, now they will produce another induced current, but now it is in the opposite direction in the previous scenario. So I understand this is not an easy thing. So I'm going to stop here and try to explain again in the different words soon.